We will now try to solve a simple problem based on stress formulation. In stress formulation, as we discussed, we start off from a stress function, we find out strains, and finally we work out the displacements. In stress formulation, we have to ensure that the displacement which are worked out are compatible with the strains. In our previous presentation, we discussed the airy stress functions. Thus, for a stress function phi, the airy stress function sigma 11 is equal to phi comma 22 plus ohm. Sigma 22 is equal to phi comma 11 plus ohm, and sigma 12 is equal to minus phi comma 12. We said that ohm is actually a potential function. We will now use this airy stress function to analyze a simply supported beam subjected to uniformly distributed loading. In this problem, we are given a stress function which is equal to ax1 square plus bx1 square x2 plus dx2 cube plus e small bracket x1 square x2 cube minus 1 by 5 x2 5. This stress field is applied on the problem shown over here. This problem tells us that we have got a beam of depth 2c simply supported at two ends having a span 2L and subjected to stress intensity Q. Please note that the stress intensity Q is in load per unit area. This is a plane stress problem. In this problem, we will use theory of elasticity to get our internal stresses and displacements, and we will show that at what point will the solution diverge from the simple beam theory. One thing which is important to keep in mind is that the boundary of this simple problem has got two conditions per face. In other words, it has got two boundary conditions per face. For example, we may specify direct and shear stress on each point of the boundary. Then for a rectangular plate, say, we could have a stress function having 8 integration constants. These integration constants will be worked out using the 8 boundary conditions. If we opt for a stress function which has got more terms and correspondingly more constants, then we will have to impose some other conditions or some additional conditions to work out our constants. One example would be that in addition to specifying axial stresses and shears at the boundaries, we can also specify moments at the boundaries. Thus, the moment conditions will also give us additional equations, which will help us to work out the unknown constants. We can also take a stress function whose unknown constants are less than 8. In that case, again, we have to make sure that all the boundary conditions are satisfied. If our number of unknown constants are less than 8, then we can use a less number of boundary conditions to find out our unknown constants. However, we have to make sure that the constants which are worked out are also satisfying the other or the remaining boundary conditions. Let us now determine the stress equations. So as we are given this stress function, we can use the airy stress function defined earlier and get our sigma x1, sigma x2, and sigma 1, 2. Sigma x1 comes out to be 6dx2 plus 6e x1 square x2 minus 4e x2 cube, where sigma x2 comes out to be 2a plus 2b x2 plus 2e x2 cube. Sigma 1, 2 is equal to minus 2bx1 minus 6cx1x2 square. Using the Airy stress function, we determine our compatibility equation. In this problem, we assume that the body force is equal to 0. Hence, the right-hand side having inverted delta square ohm would be equal to 0. So from this, we can see that delta 4 phi, when plugged well, delta 4 phi equal to 0 is satisfied. Now we will apply the boundary condition to find out these unknown constants. We will start off from the horizontal sides. Before finding out the unknown constants, it is important to appreciate that the coordinate axis we have assumed is x1, x2, and the origin of the coordinate system is corresponding to the middle of the beam. According to the convention adopted in this question, shear causing clockwise rotation is considered positive. So the vertical shear is shown causing clockwise rotation, and that is positive. Similarly, axial force or axial stresses sigma 1 and sigma 2 facing outwardly are positive. In other words, tension is considered positive. Let us now apply the boundary conditions. We start off with horizontal sides. So sigma x2 at the top horizontal side is equal to minus q according to our sign convention. Similarly, sigma 2 at x2 minus c is equal to 0. Sigma 1 2 at x2 equal to plus and minus c is equal to 0. Thus, on the horizontal side, we have only sigma 2 equal to minus q, and rest of the stresses are 0 on the horizontal side, as we can see from this figure. In the case of vertical sides, we can have at the right hand side sigma 1 2 times the cross-sectional area, which is h times dx2 integral having limit minus c till plus c equal to q times h times 2l times l. So half of this load will be resisted by the reaction at the right hand side. Similarly, the other half will be resisted by the reaction on the left hand side. Therefore, we have sigma 1 2 minus c till plus c times h dx2 is equal to plus q hl, and sigma 1 2 h dx2 is equal to minus q hl at x2 equal to minus l. The reason sigma 1 2 h dx2 is taken plus q hl is because of our sign convention. According to our sign convention, at the right hand side, our sigma 1 2 facing up will be positive. Hence, plus q is taken. However, on the left hand side, sigma 1 2 facing down will be positive. And in our case, we have got sigma 1 2 facing up. Thus, minus q hl is taken. Other conditions are that sigma 1 times the area equal to 0. So there is no axial force at the right vertical side and at the left vertical side. Hence, sigma 1 h dx2 is equal to 0 at x1 is equal to plus L, and sigma 1 h dx2 equal to 0 at x1 is equal to minus L. The final two conditions are related to the moments. Since left and right support are taken as simple supports, therefore moments at these two sides are equal to 0. Thus, we would have sigma 1 times h into dx2 times x2 integrated between minus c and plus c equal to 0. So we have got sigma 1 h dx2, which is a force, times x2, which is the lever arm, and this force is integrated between minus c and plus c, and that should be equal to 0. So that is for x1 is equal to plus L. Similarly, at x1 is equal to minus L, we will have sigma 1 h y dx2 equal to 0. Now we can put values in our equation Roman 1 and Roman 2. We will get two equations as 2a plus 2bc plus 2ec cube is equal to minus q, and 2a minus 2bc minus 2ec cube is equal to 0. So these equations are got by plugging the boundary condition sigma x2 at x2 is equal to plus c is equal to minus q, and sigma 2 at x2 is equal to minus c equal to 0. We can do the same exercise with sigma x1. So applying the first two boundary conditions, we will get two equations 1 and 2. Equation 3 and 4 give us the same answer. So we can just pick one equation. Thus 3 and 4 will give us just one equation. This equation is written as x1 minus 2b minus 6ec square, all in small bracket, equal to 0. Now we have three equations 1, 2, 3 in three unknowns, i.e. A, B, and E are unknown. Remember that C is actually half depth of the cross section. So C is known. From these three equations, we can use algebra to find out our constant E equal to Q by 8C cube, B equal to minus 3Q by 8C, and A equal to minus Q by 4. We could have done the same exercise with equation 5 till 10 and found the unknown constants and then verified the equations 1 till 4. So based on these three constants, our sigma 1 comes out to be 6d x2 plus 3q by 4c cube x1 square x2 minus q by 2 c cube x2 cube. Sigma 2 is equal to minus q by 2 minus 3q by 4c x2 plus q by 4c cube x2 cube, and sigma 1 2 is equal to plus 3q by 4c x1 minus 3q by 4c cube x1 x2. Sigma 1 2 is fully known, but it is important that we check the conditions 5 and 6. So now let us check condition 5 and 6. We can plug the value sigma 1 2 h times dx2 is equal to plus minus qhl at x is equal to plus minus l. Plugging the values, and we get left hand side equal to right hand side. Thus sigma 1 2 satisfies the condition 5 and 6. In a similar manner, our condition 7 and 8 are also satisfied. So again, we can plug the values in condition 7 and 8 and make sure that we get left hand side equal to right hand side. We have all the constants known except D. For D, we can use equation 9 and 10 and work out our constants. So using the boundary condition 9 and 10, which is sigma 1 hx2 dx2 integral minus c to plus c equal to 0 at x1 is equal to plus L, and sigma 1 hx2 dx2 minus c till plus c equal to 0 at x1 is equal to minus L. So using this condition, we would get D is equal to Q by 4C small bracket 1 by 5 minus L square by 2C square. Hence our sigma 1 is equal to 3Q by 4C small bracket 2 by 5 minus L square by C square, x2 plus 3q by 4c cube, x1 square x2 minus q by 2c cube, x2 cube. Sigma 2 is equal to minus q by 2 minus 3q by 4c x2 plus q by 4c cube x2 cube. Sigma 1 2 is finally equal to 3q by 4c x1 minus 3q by 4c cube x1 x2 square. We can also introduce moment of inertia I equal to h times 2c cube by 12, and that gives us 2 by 3 hc cube. Thus, we can bring our sigma 1 in terms of moment of inertia as equal to qh by 2I small bracket x1 square minus L square times x2 plus qh by 2I small bracket 2 by 5 c square x2 minus 2 by 3 x2 cube. Sigma 2 equal to qh by 2I 1 by 3 x2 cube minus c square x2 minus 2 by 3 c cube, whereas sigma 1 2 is equal to qh by 2I small bracket c square minus x2 square times x1. It will be very informative if we compare the results of theory of elasticity with the simple beam theory. So let us now consider a beam having the same dimensions and of the same length subjected to the UDL loading. We can take moment about point A. So we will get QHL small bracket L plus X minus QH times small bracket L plus X times L plus X small bracket divided by 2 plus M equal to 0. And that will give us M equal to minus QH by 2 small bracket L square minus X1 square. Plugging this value in the engineer's beam theory, we will get QH small bracket x1 square minus L square times x2 divided by 2I. Similarly, we can work out sigma 1 2 using well-known shear formula VQ over HI. So using the same from the same figure, we can find out our V, where V plus QL minus Q small bracket L plus X is equal to 0, and we get V equal to Qx. Now, Q is the first moment of area. So for a beam of width B and height h, our Q would be area times x bar, where x bar is the distance of the reference area, which is shown hatched, from the neutral axis. Thus, we can have V by IB for this beam times B times H by 2 minus x21, which is the area, and then we can have the distance or the lever arm worked out as x21 plus half of h by 2 minus x21. That is AQ bar, which is the first moment of area. That can be found in the Mechanics of Solid 1 playlist. So coming back to our problem, our sigma 1 2 will be equal to QH by 2I small bracket C square minus x2 square times x1. Thus, comparing the 2D elasticity results with beam theory in a tabulated manner, we can see that sigma 1, which is the axial stress in x1 direction, in 2D elasticity, that's equal to QH by 2I small bracket x1 square minus L square times x2 plus another term, which is QH by 2I 2 by 5 C x2 square minus 2 by 3 x2 cube. In the case of beam theory, sigma 1 is just equal to the first term, which is QH by 2I x1 square minus L square small bracket times x2. So theory of elasticity gives us an additional term for sigma 1. The theory of elasticity also give us stress in x2 direction, which is qh by 2i small bracket x2 cube by 3 minus c square x2 minus 2 by 3 c cube, whereas sigma 2 is 0 in the case of beam theory. Finally, the shear stress sigma 1 2 according to 2D elasticity is qh by 2i small bracket c square minus x2 square times x1, and it is similar to the beam theory, which is qh by 2i c square minus x2 small bracket times x1. So the shear stress in case of both 2D elasticity and beam theory is the same, whereas there is a difference in axial stress in both the directions. The stress 2 in the case of theory of elasticity is compressive. So sigma 2, which is the stress in the direction 2, that is 0 at the bottom, then it becomes minus q by 2 at middle, and finally it becomes minus q at the top, and that has been shown over here. This compressive stress is not available in the case of beam theory. Due to this compressive force, there is another factor getting added to sigma 1, which is the axial stress in x1 direction. So again, our x1 direction is the longitudinal direction, and that correction factor is this second term, which is qh by 2i 2 by 5 c square x2 minus 2 by 3 x2 cube. This is independent of x1. We can see that this correction factor is only dependent on x2. So that tells us that because of sigma 2, we have another factor being added to sigma 1, and that's why sigma 1 of the fiber is not simply stretching or squishing. We can work out this correction factor at plus minus c, and we see that delta sigma 1, this is plus minus q by 5. It will be interesting to find out at what length will delta sigma 1 become effective. So for that, we can work out the maximum delta sigma 1 and divide it by sigma 1 max. So sigma 1, as we know, has got two terms. We find out the maximum correction factor and divide it by sigma 1 having both the terms, and we find out the maximum of that ratio. So that has been done over here. We have sigma 1 max equal to the value given over here, q minus q h c l square by 2i 1 plus 4 by 15 c by l square. Now this term is taken by considering x1 equal to 0 and x2 equal to plus minus c. So delta sigma 1 max and sigma 1 max will give us 4 by 15 c by l whole square. Thus, from this expression, we can find that if the span to depth ratio is bigger than 3, then our engineer's beam theory will work, because the percent discrepancy is very small. However, if span to depth is less than 3, or in other words, we have a deeper beam, then the engineer's beam theory will give us inappropriate results. So we can see that for span to depth equal to 1, a square plate will give us a difference of 27%. We will now try to find out the displacement profile of this simply supported beam. So as we know, strain 1 is equal to partial u by partial x1, where u is the displacement in x1 direction. remembering that x1 is horizontal and x2 is the vertical axis. So u is the displacement along x1 direction and v is the displacement along x2 direction. So epsilon 1 is equal to partial u by partial x1 is equal to 1 by e big brackets sigma 1 minus nu sigma 2. Please note 1 by e bracket sigma 1 minus nu sigma 2 is the constitutive equation. Since we have already found the stresses, so we can value of stress 1 and stress 2. Stress 1, stress 2 and stress 1, 2 has been found above. So that will give us 1 by e qh by 2I small bracket x1 square minus L square times x2 plus qh by 2I small bracket 2 by 5 c square x2 minus 2 by 3 x2 cube minus nu qh by 2I small bracket x2 cube by 3 minus c square x2 minus 2 by 3 c cube. 1 by e is getting multiplied with all the terms. Similarly, epsilon 2 is equal to partial v by partial x2, and that is equal to 1 by e sigma 2 minus nu sigma 1, which is equal to 1 by e big bracket qh by 2I x2 cube by 3 minus c square x2 minus 2 by 3 c cube small bracket close minus gamma qh by 2I small bracket x1 square minus L square times x minus nu qh by 2I small bracket 2 by 5 c square x2 minus 2 by 3 x2 cube and big bracket closed. The shear gamma 1 2 is equal to partial u by partial x2 plus partial v by partial x1, and it's also equal to sigma 1 2 by g. So plugging the values, we'll get qh by 2gi small bracket c square minus x2 square times x1. Now we can integrate 1 and 2 in order to get displacement u. Thus u is equal to qh by 2ei x1 cube by 3 minus L square x1 all in small brackets plus qh by 2ei times small bracket 2 by 5 c square x2 minus 2 by 3 x2 cube times x1 minus nu qh by 2ei small bracket x2 cube by 3 minus c square x2 minus 2 by 3 c cube times x1 plus g1 x2. Please note we have put a constant in terms of x2 because we have integrated this equation with respect to x1. Similarly, we can write the expression for v, and a function of x1 will be added as a constant to this expression. Thus, v would be equal to qh by 2ei x2 4 power 4 by 12 minus c square x2 square by 2 minus 2 by 3 c cube x2 all in small brackets minus nu qh by 2ei small bracket x1 square minus L square times x2 square by 2 minus nu qh by 2ei small bracket 2 by 5 c square x2 square by 2 minus 2 by 3 x2 power 4 by 4 plus a function of x1. Now these values can be substituted into our shear equation. So first of all, we can find out partial u by partial x2, which is equal to qh by 2ei small bracket x1 cube by 3 minus L square x1 plus qh by 2ei small bracket 2 by 5 c square minus 2 x2 square times x1 minus nu qh by 2ei small bracket x2 square minus c square x1 plus g1 prime of x2. Similarly, partial v by partial x1, will be equal to minus nu QH by 2EI small bracket 2x1 times x2 by 2 plus g2 prime x1. Plugging values in gamma 1, 2, we get QH by 2GI small bracket C square minus x2 square times x1 equal to QH by 2EI small bracket x1 cube by 3 minus L square x1 plus QH by 2EI small bracket 2 by 5 C square minus 2x2 square times x1 minus nu QH by 2EI small bracket x2 square minus c square plus g1 prime x2 minus nu QH by 2EI times 2x1 times x1 by 2 plus g2 prime x1. So this is the expression for gamma 1, 2. We can bring all the coefficients corresponding to x1 on one side and x2 on the other side. So interchanging the terms so that terms corresponding to x1 appear on one side and the terms corresponding to x2 appear on the other. And we will get the expression which looks something like this one. This is after algebraic manipulation. So we will get QH by 2EI small bracket x1 cube by 3 minus L square x1 plus QHC square by 2EI small bracket minus 8 by 5 nu x plus g2 prime x is equal to minus g1 prime x2. Now we can call g1 prime x2 as some constant. So this expression can be integrated and we can get g1, a function g1 of x2 is equal to minus a1 x2 plus a2. Plugging value back in this equation, we can get the expression for g2 prime x. And from here, from this expression, we can get g2 of x1 by integration. So please check this expression is made equal to a1 and a1 was called as minus g1 prime of x2. So g2x is equal to minus QH by 2EI small bracket x1 power 4 by 12 minus L square x1 square by 2 plus QHC square by 2EI small bracket plus 4 by 5 plus nu by 2 times x1 square plus a1 x1 plus a3. Now, after finding out the unknown g1 prime and g2 prime functions, we can plug the values back in the expression of u and v, and we will get full expression of u and v. So the expression of u will be equal to QH by 2EI small bracket x1 cube by 3 minus L square x1 times x2 plus QH by 2EI small bracket 2 by 5 c square x2 minus 2 by 3 x1 cube minus nu QH by 2EI x2 cube by 3 minus c square x2 minus 2 by 3 c cube times x1 minus a1 x2 plus a. V will be equal to QH by 2EI small bracket x2 power 4 by 12 minus c square x2 square by 2 minus 2 by 3 c cube x2, everything in small bracket, minus nu QH by 2EI times small bracket x1 square minus L square times x2 square by 2 minus nu QH by 2EI times c square x2 square by 5 minus x2 power 4 by 6, both terms in small bracket, minus QH by 2EI times small bracket x1 power 4 by 12 minus L square x1 square by 2 plus QH c square by 2EI 4 by 5 plus nu by 2 times x1 square plus a1 x1 plus a3. Now in order to find out these unknown constants, we can make use of the boundary conditions. So the first boundary condition is that nu is equal to 0 at x1 plus L and x2 equal to 0. So the first condition is that v is equal to 0 at x1 plus L and x2 equal to 0. That means to say that there is no vertical deflection of the beam at x1 plus L and x2 equal to 0. So the neutral axis will not move. Similarly, the neutral axis will not move at x2 is equal to minus L. After this, we can have a third condition that either u is equal to 0 at x1 is equal to L and x2 is equal to 0, or u is equal to 0 at x1 minus L, x2 equal to 0. Or by symmetry, u is equal to 0 at x1 is equal to 0 and x2 is equal to 0. So in the case of this beam, we have V as a vertical deflection and U as a horizontal displacement. So obviously the neutral axis will stay 0 at the support because these are simple supports. So the first condition that V is equal to 0 at x1 is equal to plus L and x2 equal to 0 makes sense. And similarly, for the other side, we would have V is equal to 0 at x2 is equal to minus L and x2 equal to 0. In the case of displacement, in case of horizontal displacement, we can say that u is equal to 0 at x1 is equal to L and x2 equal to 0. So at the support, there is no horizontal displacement. Similarly, at the support, there is no horizontal displacement of the neutral axis on the left-hand side. In other words, the neutral axis will stay the same. It won't stretch or squish at the support. In the same manner, we can also say that due to symmetry, we can have the displacement u equal to 0 at the origin. So plugging these conditions in our displacement equations, we get our constant a1 equal to 0 and a3 equal to minus 5 by 12 QHL by 2EI minus QHC square L square by 2EI small bracket 4 by 5 plus nu by 2. This will give us the expression for the displacement u and displacement v. The displacement u is equal to QH by 2EI, big bracket, small bracket, x cubed by 3 minus L square x1 times x2 plus small bracket 2 by 5 c square x2 minus 2 by 3 x2 cubed times x minus nu x2 cubed by 3 minus c square minus 2 by 3 c cubed, three terms in the small bracket, and then we big bracket close. Similarly, V would be equal to QH by 2EI, big bracket x2 4 by 12 minus c square x2 square by 2 minus 2 by 3 c square x2 minus nu, big bracket x1 square minus L square in small bracket times x2 square by 2 minus x2 power 4 by 6 plus c square x2 square by 5. So we have all these terms getting multiplied with QH by 2EI. And then we have QH by 2EI again getting multiplied with these terms. So that is L square x1 square minus 1 by 12 x1 power 4 plus 5L4 both in small bracket plus c square small bracket 4 by 5 plus nu by 2 and then multiplied by another small bracket x1 square minus L square and then the big bracket closed. It is important to notice that the central line of the beam, which is shown in this figure, is not the neutral axis, remembering that neutral axis will always have stresses equal to 0. And the reason that this is not the neutral axis is that there is a compression stress as we saw over here. So the axial stress in the x2 direction, sigma 2, produces compression force at the neutral axis, which in turn produces tensile strain or displacement of the neutral axis in the x1 direction. It is because of this reason that if we try to find out the horizontal displacement of the neutral axis by plugging x2 equal to 0, we will get nu qx by 2e. So that clearly shows that there is a stretching of the central line. The deflection of the central line V is equal to QH by 2E big bracket L square x1 square minus 1 by 12 x1 power 4 plus 5L 4 both in small bracket plus C square small bracket 4 by 5 plus nu by 2 small bracket times small bracket x square minus L square. And the maximum deflection is at x1 equal to 0. So plugging the values x1 equal to 0 and x2 equal to 0, we'll get minus 5 by 24 QH L4 by EI times 1 plus 12 by 5 C square by L square times small bracket 4 by 5 plus nu by 2. According to simple beam theory, the maximum deflection, such sort of simple supported beam, is 5 by 24 QH L power 4 by EI. So correction deflection according to the 2D elasticity will come out to be 12 by 5 small bracket 4 by 5 minus nu by 2 times C by L square. So this is coming out from this term. The second term is the correction deflection. So if we take nu is equal to 0.3, which is for steel, put the values in this equation, we can get that span to depth ratio where the beam theory will give us adequate answer. So if span to depth is equal to 5, the discrepancy is almost 9%. If it becomes 4, the discrepancy is almost 14%. If it becomes 3, the discrepancy is 25%. If span to depth is 2, discrepancy shoots up to 57%. And finally, if span to depth is the same, the discrepancy in the deflections goes exponentially to 230%. So we clearly know that in the case of stresses, we could have gone higher than span to depth ratio of 3 and use simple beam theory. However, the deflection, even in case of simple beam theory, is having a very high percentage of discrepancy.